This is my General Electric 8-cycle 2-speed clothes washer, and I've always wondered what this switch does. It says 2 speeds, so let's see if that works any different. Okay, so this is load number 2. Gonna let my battery voltage come up here, 13.7 volts, and I also turned the machine down to the slow cycle. And that looks like it's a little less power, so we'll see how this one goes. And there was the starting kilowatt hours, 2.43, so we'll take a look at that, see if there's any difference. So yeah, I'll let this run, and I'll maybe check back when it starts that first spin cycle. And there we go. Okay, that works a lot better. I think I will just use the low speed on the inverter, and we'll see if there's any less power consumption over the runtime. And 8 amps of AC current. And again, if I pull the power factor capacitor out of there, that jumps up to 9.3. What else do we have? 546 watts, 970 volt amps, and 0.56 power factor. You can see now it's shut down. Might try to calculate the proper size run capacitor to correct the power factor on this, and then just see if I can get in the washer and wire it in parallel with the motor. And in fact, I think I'd probably need more than 30 microfarads, so I'll run the numbers on this and see what kind of run capacitor that particular motor would need. So let's take a look at those power factor numbers that we measured on the video. This is on rapidtables.com. It's their power factor calculator, and I'll put a link to this in the video description if you want to check it out. Pretty easy to use. I'm running single phase. I entered the power that the kilowatt meter measured, 546 watts, 9.3 amps. I hit calculate, and down here at the bottom gives you a value of a correction capacitor that would correct the power factor on this washing machine motor. And it says about 180 microfarad. And then just as a data point from the video, I plugged in a capacitor and it dropped my current to 8.05 amps. And you can see down here the correction capacitor is now about 150 microfarads. It was 180. The difference is 30, and that happens to be the size of capacitor I plugged in. The other data point here is the kilowatt meter was, I think, measuring 970 volt amps, and this calculator is saying 966 with that capacitor plugged in, so that lines up as well. If we were to fully correct the power factor of that washing machine motor, I just happen to know that 4.55 amps brings the power factor to unity, and my current I've dropped from 9.3 amps down to 4.55 amps, better than a 50% reduction just by plugging in a capacitor. I haven't had to increase my inverter size, I haven't had to add solar panels or charge controllers, just the price of a capacitor. The conventional wisdom is that power factor really doesn't matter for residential loads because you're not billed for the reactive power that you consume, because it's not real power. If you were to run this washing machine for an hour, and you would be billed for 0.546 kilowatt hours. The apparent power is over 1,000 volt amps, but you're not billed for that. But if you are running that same device off of a power inverter, you essentially are paying for kVA because your inverter needs to generate all of this apparent power. In this case, I've got a power inverter and I've got a washing machine plugged into it. The only way to make that washing machine motor run is to provide 1.116 kVA of apparent power to get it to go. Or I could come in and add this correction capacitor, which would provide this reactive power to operate the motor. If you're running inductive loads off of a power inverter, you may want to consider power factor because it does matter. Now this applies to my particular inverter, which uses a transformer to produce the output voltage. So the inverter has 12 volt DC on the input. It has 4 power MOSFET transistors that are set up in what's called an H bridge, and they basically modulate the incoming voltage and current to produce a 12 volt AC waveform that goes through the transformer with about a 10-to-1 ratio, boosting the voltage to 120, but at the same time the current is cut down by a factor of 10. So each inverter is going to handle inductive loads differently. You can take these simple measurements, like in my case I measured 9.3 amps and 546 watts, and that will tell me exactly what I would have to do to correct that power factor with that inverter. So anyway, let's go back to the video and see what the energy consumption was at the slow gentle cycle and see if that improved over the fast cycle that we ran in the first video. Okay, YouTube, looks like the second load of clothes finished. Let's see, 2.68. So yeah, that uses less power. I think it was 2.43, so that's only 250 watt hours for a load of clothes instead of about 300 on the fast cycle, and the inverter seemed to be a lot happier this time. Yeah, it looks like that is the key. So if I run this on slow speed, there's apparently a gear reduction mode in the gearbox in the washer, and it takes less power to run at the slow speed. So I did not know that before. If you're plugged into the utility power, I never know how much power anything takes. But when you try to power it yourself, you find out all these little tricks. So I can make my washer a little more inverter friendly by running it on the slow speed. If you have any questions, put that in the comments section below. If you haven't already, subscribe to my channel for updates. And as always, thanks for watching.